In the previous lecture, we were talking about general schemes we could have to simplify a logic expression. So we talked about a few rationales. We said we may want to reduce the number of literals. We may want to reduce the number of transistors. We may want to reduce the number of logic gates. So there are a number of ways a person who is designing the logic circuit, they could go about choosing their own rationale depending on the design constraints. Maybe they have constraints in the number of gates. Maybe they have constraints in the number of the amount of space they have for that digital logic design. So depending on the constraints they have, they will choose their own rationale. There is no one formula of reducing expressions. But if you have a complex expression with a lot of logic gates and a lot of literals, in general, you could say that if you reduce the number of literals and the number of logic gates, you have done a pretty good job simplifying the logic expression. And you could go as low as possible. So in the homeworks and such, you have been attempting some Boolean algebra problems which involve logic expression simplification. But the problem while using Boolean algebra is there is no good way to know when to stop. There is no good way to be sure that the last expression you have is absolutely the simplest expression. Although with a lot of practice, you might be able to visually inspect and say, yeah, this is the best I can do because no other step further can be applied. However, there is no systematic way to know that that is the simplest form. So we are going to slightly move away from a Boolean algebra approach to a Karnaugh map approach, which is essentially a systematic way to minimize logic expressions. So there will be a set of rules that I will lay out today, and if you follow all the rules, then you will be guaranteed the simplest form of logic expression. So it is systematic, it is structured, and it guarantees you the simplest form as long as you follow the rules correctly. How is it different from Boolean algebra? Well, Boolean algebra is simply writing out expressions, but K-map is a graphical approach to minimization. So I can say this is a graphical approach. So it tends to be a little bit easier than Boolean algebra because of its graphical nature. Now let's talk about some notes here. Note 1. Logic expressions are not unique. We talked about this while we were discussing Boolean algebra. When you have logic expressions, you can express them in many different ways. Logic expressions are not unique. Now, note 2, which is a little bit more important and more relevant for our discussion here today, the simplest form of the logic expressions is also not unique. So you may have different simplest form. They are representing the same logic function. However, they look different. But the point to note is they will have the same minimized form, meaning if you were to associate a term of cost of implementation with these logic expressions, the cost will be the same, but the form itself might be different. And we'll talk about more about the various forms of simplified logic expressions you might get and how they are not unique. So when we are doing some examples, I will talk more about note 2. All right, so what is a K-map? A K-map or a Karnaugh map is a grid view of a truth table. So you're essentially taking a truth table and then breaking it into rows and columns, and that makes it into a grid view. All your input variables, no matter how many you have, we will be looking at 2 input variable, 3 input, 4 input, and 5 input variable K-maps. All those input variables are distributed on rows and columns of that grid. Now the grid itself will contain several cells, and in each cell you could have the entry of 0 if the logic expression is false over there. You could have the entry of 1 which is true over there, or you could have the entry of don't care, which means that that particular input configuration, the designer doesn't care about that. So the output could be a 0, could be a 1, it doesn't matter. So usually you will see a 0 or a 1, but you may also see a don't care situation in that case for a cell. The cell entries, those are essentially evaluating the output variable for that specific row and column input variables. And as you might be able to guess by now, you will have one K-map for one output variable. So if you have 5 output variables for a logic expression, then you will have 5 K-maps that result from that. We will be focusing on the 2 variable K-map all the way to 5 variable K-map. And in my opinion, the difficulty increases as you go higher. So 2, 3, 4, these are pretty standard and very easy to tackle. But the 5 variable K-map, they are the same concepts. However, because of the number of cells increasing, it is not as straightforward as the 2, 3, 4 variable K-maps. Questions so far? Now, there is an underlying Boolean arithmetic behind the question, what makes K-maps possible? So the underlying reasoning is very important to understand, because we can apply that. We can apply that for every K-map simplification that we do. So consider this. So I'm going to say consider some function f, which is x and y, or x and y complement. So if you have this logic expression and you're asked to minimize this logic expression, the first step you probably will do is you will probably factor out the common Boolean variable, which in this case happens to be x. And inside the parentheses, you will be left with y or y complement. Y or y complement is simply true. So this will simplify to x and 1. We know that is simply x. Now notice what happened here. I want you guys to notice the change between the original expression and the expression that we ended up with. We started with this, and we ended up with x. Now, if I wanted to summarize this into one statement, I could probably say the variable that changed got eliminated. And in this case, the variable was y. So between the two product terms, we had y and y complement. X was remaining the same. So one variable was changing, one variable was remaining the same. So when you simplified it, you simply had the variable that remained the same. The variable that changed got eliminated. This is the underlying Boolean algebra that supports K-maps. In fact, we leverage that when we use K-maps. So another example that we could write is f say equals a and b complement and c, or abc, and I apply the same logic and I see that there's a b there, there's a b complement and b there, so it gets eliminated and you get a and c there. Right. So the variable that changes gets eliminated, the variables that remain the same, they continue to appear. So that is the underlying Boolean algebra which is exploited by K-maps. All right. Another thing to note over here, we are allowing one variable to change. We are not allowing multiple to change at the same time. So what that means is if this was C complement and B complement, B changed, C also changed, then we wouldn't be able to do this. So we require some to remain the same, some to change. Now I'm going to first summarize all the rules. And these are the rules that need to be applied to determine the simplest sum of product expressions. When you are doing K-map simplification to obtain simplest SOP form, then you will be combining the ones in the K-map. So inside those cells in a grid view, you will have cells. Inside the cells, you will be focusing on the ones. You will be trying to combine the ones in the K-map to get the simplest SOP expression. So I'm going to just run through the list here, say it one time, but you are going to see this being used and applied to all the examples. But I feel like if I lay out all the rules at the beginning, it's a little bit better as opposed to doing the examples first and then laying out the rules. So rule number 1, group adjacent ones. And that ones is because we are focusing on the SOP expression. The size of each group can be 1, 2, 4, 8, or it has to be in general powers of 2. Next rule is you have to cover all the ones, meaning when you group the adjacent ones, you have to group all the ones. You cannot leave any one. The group should be that this cover all the ones simply means the group should be over all the ones in the K-map. A diagonal is not adjacent. So you need to group adjacent ones. Diagonal is not adjacent. Because in a diagonal, two variables change at the same time, which is not allowed. We only need one variable to change. The K-map is a grid view, and that grid has edges that wrap around. Those edges wrap around both horizontally as well as vertically. So think of it as a cylinder as opposed to a rectangle. Next rule, can combine 4 corners in one group. This applies for 3 and 4 variable K-maps. As we are applying these rules to several examples, they will become more and more clear. But right now, these are the complete set of rules. Can combine the 4 corners in one group of adjacent ones. The last rule here is treat the don't care as a 1 only if it helps you make a larger group. Otherwise, treat it as a 0. Because it's a don't care, it could go either way. It could be a 1, it could be a 0. So treat it as a 1 only if it helps you make a larger group. So those are all the set of rules for SOP expression. Now we can simply change the ones to zeros. Where is and here and here. So everything that is highlighted, if we change them from ones to zeros and zeros to ones, you will get the rules to determine POS expression. which is laid out right here. So all the ones are replaced with zeros, as you can see. So you're grouping adjacent zeros here. The size of the groups still needs to be a power of 2. You need to cover all the zeros. This also needs to change. The group should be all over the zeros. And then treat the don't care as a 0 only if it helps you make a larger group, otherwise treat it as a 1. So all the zeros and ones are flipped. That way you get the simplest product of some expression. So those are the rules. And while you are applying all these rules, you need to do these, you need to keep these things in mind. So the goal during K-map simplification should be make the largest possible groups of adjacent ones or zeros, depending on SOP or POS. So make the largest possible groups, reuse cells in a group in order to make larger groups. So you're trying to make larger and larger groups, and while you're making larger groups, you may need to reuse cells, and you should reuse cells to make larger groups. So the goal is to make largest groups of ones. And if you do this, you might end up with the fewest number of groups. So your goal is to make as large as possible of a group as possible, which will in turn give you the fewest number of groups as possible. And if you do make fewest number of groups, that essentially means that we have fewest number of terms, either the product terms or the sum terms, in the final expression. And if you make a bigger group, our goal was to make a large group. So if you make a bigger group, then that results into a smaller resulting term for that group. You will see all of this playing out in the examples. But those are your goals. Make as large of a group as possible, as fewest of the groups as possible. Let's start with the two variable K-map. So what do you have for a two variable K-map? Well, let's start with some arbitrary truth table over here, and we will transition that truth table into a grid. Because I have two inputs, x and y, I'm going to lay out that x and y onto, x is for the columns and y is for the rows. I could have switched it around, it doesn't really matter. Now let me call the output f over here. Next, I will fill out the truth table 0 0 0 1 1 0 1 1, and what I'll do is I will simply write out the min terms here. For reference, I will say this is min term 0, min term 1, min term 2, min term 3. And as you know, these might be zeros, these might be ones, these might actually be also don't cares. That's my output. Now, if I transition this particular truth table into a K-map, how does it look like? So x, which is for the two columns here, it could have the value of 0 or 1. And the same applies for y. Y could also have a value of 0 or 1. Now when x is 0, y is 0, f is min term 0. So let me put min term 0 right here. So this guy went over there. And similarly, I can say when x is 0 and y is 1, you have min term 1, min term 2, and min term 3. So those are essentially where those particular terms will lie. And as you know, these could be zeros in here, or these could be ones in here, or some of them could be zeros, some of them ones, some of them in fact even be don't cares. So in order to run through an example here, we'll try to put some numbers in here. So let's see, I will put some arbitrary 1010 here. So I don't have don't cares, I simply have ones and zeros. If I fill it up, how does it fill it up? It goes 1010. Now the first question you ask is, question 1, can I make a group of four ones? Now the question is, why did I stop at 4 ones? Well, because the biggest group of 4 ones, biggest group of ones you can make is 4. So I have to stop at 4. So the first question is related to your main objective. Your main objective is to make the largest group of ones in the case of SOP. So we are doing this for SOP here. We will be doing the first few examples on SOP, then at the end we will talk about POS. So for now, just assume that I'm talking about SOP simplification. So can I make a group of 4 ones? No, I can't, because there are only 2 ones in there. So the next question would be, how about 2 ones? Can I make that? Yes, I can make that. And notice it goes down from 4 to 2 to 1. Powers of 2, and it is going down. So yes, I can make a group of 2 ones. Where are they? Let me put a box around it. Maybe this one will be better. That is my group. It is adjacent. It is not diagonal. And I am covering all the ones. I have not left out any ones. So I'm done. I have grouped adjacent ones here. So what is the resulting term in this? The resulting product term for this is y is 0 for that row, x changes, x gets eliminated. So this is simply y complement, because y is 0 over there. So your answer for this is going to be f equals y complement. That is the simplest SOP expression. As you can see, we covered all the ones here. The blue group covers all the ones in the K-map, the 2 variable K-map. So we are done. We don't need to do any more groups. That's it. One group of 2 ones. That's all we need for this. Now let's do another example here. How about this? Let me take this guy from here. All right, so I will keep the skeleton as is, and I will write this, and I will also do one more so that you can see me do a couple of exercises here. Let's do 1 1 1. All right. All right, there are a couple of questions in the chat box, and I think those will be addressed in these 2 examples. So let's suppose that instead of this particular truth table for the logic expression, you had some other f's. So you had 1 0 0 0 and then 1 1 1 0. So those two examples I've laid out over here in these two variable K-maps. So what would be the expression over here? Again, my goal is to find simplest SOP for F. Let's focus on the first one. Can I make a group of 4 ones? No. Can I make a group of 2 ones? No. Can I make a group of 1 1? Yes. Where is that? Right here. So this guy doesn't have any friends. It is by itself. Nothing to combine here. So what would be F? X is 0 and Y is 0. That's it. So your F for the first example is simply X bar and Y bar. Also written as X nor Y. How about this guy? Next example. Can I make a group of 4 ones? No. Can I make a group of 2 ones? Yes, 2 of them, in fact. So you can make this guy and you can also make this guy. So you have 2 groups of 2 ones in this case. What would be the expression for this? X is 1, Y changes. So X is 1, Y changes. Y changes, Y gets eliminated. X is 1. That's it. How about the blue group? Y is 0, X changes. Y complement. So the simplest expression for the second case is X or Y complement. Notice you are writing it in the sum of product form here. So you write each of these terms as products and then you sum everything up at the end. So you're going from truth table to a grid view to forming groups and writing out each group as a product term in the case of SOP. Those are the principles that you will see repeatedly from 2 variable K-map all the way to 5 variable K-map. Questions here? All right, let's move on. 2 variable is done. Let's move on to a 3 variable. Now a 3 variable K-map is the truth table for a 3 variable K-map is going to look like this. I have chosen A, B, C as my 3 input variables, and F is my output variable. I have distributed A and B across 4 different columns, and I have distributed C across the 2 rows. So I have transitioned a truth table into a grid view. I have 8 entries in the truth table, so those give me the 8 cells in the K-map. Now, a couple of things I want you to note here. Could I have drawn the K-map this way? And done this B, A, C? Yeah, sure, I can do that. But then becomes very difficult for me to kind of keep track of where each f is going to go, because I have switched around the input variables. But the point I'm trying to make is you can lay this K-map horizontally, you can lay this K-map vertically. The way I show at the top is just my convenience. And my convenience is also A followed by, let's see, A followed by B followed by C goes A followed by B followed by C. So that allows me to get a pattern out of this. And I will show you what that pattern is. But that pattern is not possible with an arrangement like this. It would take me a lot of time to fill out the cells in the vertical K-map that is shown at the bottom. So I'm not going to use this for now. But I want to let you know that you could use it if you wanted to. Now let me show you the pattern that I was referring to. Oh, by the way, I hope you recognize this change here. A and B are two input variables, and we have 4 columns here. And if we have 4 columns, we have 4 possibilities for A and B: 0, 0, 0, 1, 1, 1, and 1, 0. Notice 1, 1 is ahead. Why is this the way this is? Why is the skeleton of a 3 variable K-map laid out this way? Anyone? Why did we go from 0, 0 to 0, 1 to 1, 1 to 1, 0, right? So why is this not 1, 0 and 1, 1? The usual 0, 1, 2, 3, right? You're right, absolutely right, Charles. This is gray code. Why are we using gray code for this? Alex, you're absolutely right. This is done because we said only one variable can change at a time. So if you want to make things adjacent, you have to change only one variable between any 2 rows or any 2 columns. So 0, 0 changes to 0, 1, 0, 1 changes to 1, 1, 1, 1 changes to 1, 0. While you are doing that, only one variable is changing. Also note that I said edges wrap around. So 1, 0 and 0, 0 are also adjacent because only one variable is changing here. All right, so let's come back to the pattern question I said. What I'll do is I will number these. I will number these as 0, 1, 2, 3, 4, 5, 6, and 7. So once I number them, I can also number them inside the K-map. So I can go 0, 1, 2, 3, 4, 5, 6, 7. I've numbered each row in the truth table with its decimal equivalent, and that allowed me to reference each cell with that specific decimal number. This now is in a pattern. So if I follow the same sequence of having my inputs in this order A, B, C, and then laying out my K-map in this form, all I need to do is follow that sequence. So that will make it faster for me. It will make things much faster for me. So what do I have? 0, 1. Now I'm going to fill out the K-map here. 0, 1, 1, 0. Followed by 1, 0, 1, 1. So if you do this, you are exploiting the patterns and you are able to transition from a truth table to a K-map much faster. All right, so let me go back here, zoom out, and let's talk about the questions that we need to ask in the case of 3 variable K-map. Question 1, can I make a group of 8 ones? The answer would be no, because you have at least 1 0 in there. The next question is, can I make a group of 4 ones? I want you guys to kind of participate so that this goes well. Can I make a group of 4 ones? The answer to that is also no. I can't make a group of 4 ones. So I will have to resort to making groups of 2 ones. So let's start with making groups of 2. Let's focus on this guy. Can I make a group for this? Yes, I can make a group right here. How about for this guy? Cell number 7. Cell number 7 can only be combined with cell number 6. How about cell number 2? Cell number 2 can only be combined with cell number 6. How about cell number 1? Cell number 1 is alone. It doesn't have any friend. I cannot combine it with anything. Now, just to make sure that you understand adjacencies, I'm going to highlight the adjacencies for cell number 1. What are things that are adjacent to cell number 1? Let me shade that in gray. So focus on cell number 1 right here. Cell number 1. The adjacencies for cell number 1 are this guy, this guy, this guy. 3 adjacencies in a 3 variable K-map. But all those 3 adjacencies are zeros, which is why it doesn't have any 1 to combine with. So let me erase that out here and go back to writing the expressions for each of the groups. So how about for this guy? What is the product term for that particular singleton? It's called singleton. Nothing is able to combine here. So for that particular one, you would say F, or the product term is A complement, B complement, C. Because A is 0, B is 0, and C is 1. How about for this guy? The vertical group of 2 ones. A is 1, B is 1, C changes, so it gets eliminated. Next, this group. For that group, A is 1, B changes, so it gets eliminated, C is 0. How about this one? A changes, eliminates, B is 1, C is 0. So if you combine all of this, what do you have? You have F equals A and B, A and C complement, B and C complement, A complement and B complement, and C. That is your simplest answer, simplest sum of product solution. Now, if this was being done using Boolean algebra and you stopped here, you wouldn't know very quickly whether this is the simplest form or not. But because we have used K-maps, this guarantees us that this is the simplest one. All right, so there's a question in the chat box. Says cell 5 is adjacent to cell 1 because of the wraparound rule you were talking about. Cell 5 is adjacent to cell 1. Yes, you are right. It is adjacent to cell 1 because of the wraparound rule. All right, let's see here. Uh, Cell 5 is adjacent to cell 1, and also cell 0 is adjacent to cell 4. And also cell 0, 1 is adjacent to cell 4 and 5. We'll talk more in other examples. But let me take questions about this one first. Questions about this particular example of 3-variable K-map. All right, let's see here. Another example. This is again a 3-variable example. My goal is to find the simplest SOP. You start asking the question, can I make a group of 8 ones? The answer would be no, because you have 2 zeros. At least 1 zero would have been done. So you cannot make any group of 8 ones. So can you make a group of 4 ones? Yes. How many? Oh, that's one. You are right. You can make 2 groups of 4 ones. Because this is done, now I'm going to my goal is to make larger groups of ones. Even if that means I have to reuse cells, that's fine. They wrap around. Absolutely right. So I'm going to wrap around this way. Let me draw a little bit better here. And this way. So I'm going to get 2 groups of 4 ones. That's it. I have covered all the ones, so I can stop here. What would be the terms? For this guy, for the horizontal group of 4 ones, what do you have? You have C is 1, A and B change. So C is 1. That's it. C. How about for this guy, the wraparound one? A changes, B is 0, C changes. So that's simply B complement. So your simplest expression here is B complement or C. Done. So you can combine, well, in this case, you could also say I can combine the 4 corners. Right, so that's essentially the same thing as edges wrapping around in this case, in the 3-variable case. Now, I want you guys to notice something here. When you made a group of 4 ones, you got 1 literal per product term. When you had a group of 2 ones, you had 2 literals per product term. When you had a group of 1 with only 1 1, you had 3 literals per product term. So I hope you see that the bigger the group you make, the smaller the product term you will get. In the case of SOP, the same thing that will transition to the bigger group of zeros you make, the smaller the sum term will be for POS simplification. That is coming up later. All right, questions about these 2 examples for the 3-variable K-maps? All right, next, I want to talk about a backdoor connection between Boolean algebra and K-maps. Now, this is a trick. This is This is a very good understanding of K-maps and Boolean algebra, but I want to show you how you connect the two. So consider this. Consider a Boolean expression f equals x and y complement, or x and y, or x complement and y. So I'm going to try to work in Boolean algebra world and K-map world for the same logic function f. So what I'll do first is I will fill out the K-map for this particular logic function. So I will highlight these first. So let's say this is blue, and say pink here, and say yellow here, right? The first product term for f is x and y complement. So where should I put a 1? I should put a 1 when x is a 1, y is a 0, right there. Next, x is a 1, y is also a 1, right there. Next, x is a 0, y is a 1. So for those three terms, I have filled out the K-map. Now, when you do the K-map, what do? You are trying to group the ones, right? Okay. By the way, this, if it is empty, it is 0. Now, when you group in the K-maps, what do? The first question you ask for a 2-variable K-map is, can you make a group of 4 ones? The answer is no. Can you make a group of 2 ones? The answer is yes. Where are those 2 groups? They are here and they are here. Now I want you to notice something here. This particular cell, the one in the pink, was reused. The term, which term was that? The pink term was x and y. Do you guys see that? The pink term, the pink one, is being used in 2 cells for combining adjacent ones. How does that transition into Boolean algebra? That transitions as, take this term x and y and duplicate it. Because you don't know which term to duplicate so that you can combine more. We learned that some of the techniques in Boolean algebra involved forcing the missing literal, duplicating terms in order to combine more. But how do you know which term to duplicate? Well, now you know. By using the K-map background, you can understand which term are you going to be able to duplicate so that you can combine more. So what do you duplicate? You duplicate x and y as simply x and y, x and y. You are going to use it only in two cells, so you only combine twice. You duplicate only twice. You will leave the rest as is. The next step would be to combine them. Pull out an x from the first two, you get y complement or y. Pull out a y from the next two, you get x or x complement. This goes to a 1, this goes to a 1, you get x or y, which is the same as this. This is x, this is y. So I hope that discussion, by having Boolean algebra and K-maps side by side, you were able to understand some intricacies in Boolean algebra and how they can be better viewed by looking at a graphical K-map. All right, so let's move on here to a 4-variable K-map. Now, 4-variable K-map will, of course, have 16 cells, and the input variables are, you know what, let's do the pattern here. So let me move this by the side for now. And what I'll do is I will say this is A, this is B, this is C, this is D. Those are my 4 inputs. And then I have my output F, for example. And I'm going 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, so on up to 1, 1, 1, 1. Right. So I'm going to number them, say 0, 1, 2, all the way to 15. So I've essentially indexed the output column. So where are those going to be in the K-map? Those are going to be here. The strategy that we used for AB, which is 0, 0, 0, 1, 1, 1, 1, 0. Now, because you have 4 rows, the same strategy applies over here, 0, 0, 0, 1, 1, 1, 1, 0. And the numbers go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if you are familiar with the order here to the order inside the K-map, if you have a pattern about it, it will make your life much easier. So I hope that was helpful. Next, let's move on to our conversation of combining the ones. Can I make a group of 16 ones? The empty cells indicate 0. I cannot make a group of 16 ones. So the next question is, can I make a group of 4 ones? Can I make a group of 4 ones? Yes, you are right. So let's try to make a group of, the next questions would be, right. Kevin, you're right. I should say 16 down to 8. Can I make a group of 8 ones? The answer is no. So I jumped the gun over there. Yes, you can only make a group of 4 ones in this case. Thank you for catching that. Next, so let's try to answer which groups of 4 ones we can make. Edges wrap around. So my first group that I see is right here. I'm going to make that right here. Let's say that's my first group. Edges wrap around. The 4 corners, absolutely right. So I'll make the 4 corners here. 1, 2, 3, and 4. So the 4 corners are done. Cell number 0, 1, 8, 9 are done. What else is remaining? How about cells 15 and 14? 15 and 14, right? So I'm done with group of 4 ones. That's it. I cannot make any further group of 4 ones. Only 2 of them. Next, I go down to 2 ones. For 2 ones, what do I have? Notice cell number 15 can only be combined with cell number 14. Cell number 14 has other options though. Cell number 14 can be combined with cell number 12 also. 12, 8, 14, 10. 12, 8, 14, 10. You can make that. However, let's see. This guy can only go with this guy, but this guy can be combined with, oh, you're right. I missed that one. Another group of 4 ones is possible. That and that. Yes, you can make a third group of 4 ones. Any other possible? I think that's it. Now you can make groups of 2 ones. Let's start with 15. 15 can only be combined with 14. 5 is left. Cell number 5 can only be combined with cell number 1. That's it. That's going to give you the simplest expression. So let's write out the simplest terms here. Let's say for the 4 corners, what are you going to get? For the 4 corners, B is 0 and D is 0. That's for the 4 corners. How about this group right here? The first group we made, 0, 1, 8, 9. B is 0 and C is 0. How about the last group of 4 ones, which was the one that I overlooked? 12, 8, 14, 10. That is, let's see, A is 1 and D is 0. Now let's move on to the groups of 2 ones. 15 and 14. Let's see, C is 1, A is 1, B is 1. How about this guy? Cell number 1 and 5. A is 0, B changes, C is 0, D is 1. So that will be your, so sum of all those terms will be your resulting answer. So F is, let's see, B complement and D complement, or B complement and C complement, or A and D complement, A, B, C, A complement, C complement, D. So there are 5. 1, 2, 3, 4, 5. 5 product terms in this. That's your simplest SOP expression. Questions about this example? All right, let's move on to don't cares. So now in another 4 variable K-map example, I have put don't cares in this. So remember, you will treat the don't care as 1 only if it helps you make a bigger group. Otherwise, you treat it as a 0. So your goal should be to make as big of a group as possible to cover all the ones. Note over here, I should say this maybe. Your goal is to cover all ones. It is not to cover all don't cares. So you can leave out the don't cares if they are not being used to make a bigger group, in which case they are being treated as a 0, which is fine. Your goal is to cover all the ones, not to cover all the don't cares. So how about this? Let us start with group of 16 ones. Are there any group of 16 ones that are possible? No. How about 8 ones? Can I make a group of 8? Yes, the answer is no. I cannot make any group of 8. So I have to go down. One more. Can I make a group of 4 ones or 4 adjacencies? Three one inclusive groups of 4 are possible. So Parker says that there are there are 3 groups, 3 such groups of 4 are possible. Let's try to identify them. There is one group that is kind of very apparent to me, which is right here, right in the middle. Come on. And I'm going to draw that because this particular one cannot be combined with other things. So for me, that is a very good group of 4. How about next? How about this particular one? Can I combine it with as a group of 4? 4 possible groups. Only 3 are required. That's what Parker says. All right. So next, let us make a group of 4 here. That guy and that guy. Edges wrap around. So I'll be able to combine those 4 ones. Next, focus on the top right corner. For that particular top right corner, you can make a really big group by actually combining 4 ones right here. So you have treated those 2 don't cares as ones here. How about this guy? This guy is still left, right? That one. Who can you combine that with? The only place you can combine that with is a group of 2 there. What else is left? This particular one is left. Who can you combine this with? Well, the only place you can combine it with is right here. Are there any other groups that you would need to make? Can you do the corners? No. You either have to do the 4 corners or that's it. You cannot do 2 of these because you can see that multiple things change while you're doing that, those 2. So you cannot just do those 2, you have to do all 4. Just 2 corners would count as diagonal. Diagonal is not adjacent. Now, an important question is, would you try to make a group here vertically? No, because your goal is not to cover all the don't cares. So you would leave that don't care out, which is essentially means that you are treating this as a 0 and all of this as a 1. All right, let's write out the answer here. Let's write out each product term. So for this guy, you have D and B complement. Let's see, for this guy, you have A and C complement. Let's see, for this guy, you have, what is that? B is a 1, C is a 0, D is a 0. Let's see, for next guy here, A is a 0, B is a 0, C is a 1. Did I get them all? 1, 2, 3, 4. Oh, the horizontal one is, I left out the horizontal one. C is a 1, D is a 1. So if you put everything together here, you get your F. All right. Let's move on to a 5 variable K-map. Now for a 5 variable K-map, you cannot put everything on one particular grid. So what you do is you introduce two 4 variable K-maps. That's your 5 variable K-map. So what you can do is this. Actually, you see, let me change a few things here. If I want the, so let's see here. Say I have A, B, C, D, and E, and this is F. I'm going 0, 0, 0, 0, 0, 0, 1, blah, 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 1, 1, 1, 1, 1. And there are what? 32 entries in this. So those are numbered what? 0, 1, 2, all the way to 31. So what I'm going to do is I'm going to use these 4 as input variables for each of the 4 variable K-map, and then I will use A to identify which 4 variable K-map they go into. So B, C, D, E. So I'll say this guy is B, C, D, E here, and then B, C, D, E over here, and then this is A is 0, A is 1. So that way, the first 16 entries go into the left K-map, and then the last 16 entries will go into the right K-map. So let's also number them. Like we did in the truth table 0 to 31, let's also do this over here. Let's see. 0, 1, 2, oh, not 2, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Similarly, 16 starts here. And then 23, 28, all right, so that finishes up all the 31 locations. Notice this is subject to the order of the inputs you choose. Earlier, I hope you understand why I made that change to E, from E to A. If I was doing E here, E is the least significant input, so it's going 0, 1, 0, 1, 0, 1. So if I continue to use that way, I would have to go left K-map, right K-map, left K-map, right K-map for the numbering. I didn't want that to happen, so I changed that in such a way that I have first 16 going to the left K-map, and then the right the next 16, the last 16 going to the right K-map. Okay, so once you have this, and I have chosen some locations where it is a 1 here. So the first question you will ask is, can I make a group of 32 ones? And of course the answer will be no. Next question is, can I make a group of 16 ones? The answer should still be no. Can I make a group of 8 ones? I'm going to take a moment here. Can I make a group of 8 ones here? Yes, you are absolutely right. The group of 8 ones is actually this. So that's the only group of 8 ones you can make. Next, can I make a group of 4 ones? Or you can also start thinking this way. This particular one, cell number 15, how can I combine it with anyone? The only place I have to combine that is this. How about this guy? 27. 27 can only be combined with 26. How about 10? Cell number 10, can it be combined with anyone? 26. Absolutely right. So let's write out the terms here. What are you going to get for the group of 8 ones? A is changing. B is 0. C is a 1. D is a 0. And E is changing. So you get B complement, C, and D complement. Let's see. D is a 0 there. Yes. C is a 1 there. Yes. And B is changing, E is changing, A is changing. Is B changing? Yes. 0 to 1. 0 to 1. Oh, yeah. Let me verify this again. C is a 1. Yes. C is a 1. Yes. D is a 0. 0. D complement. Yes. A is changing. B is changing. Yes. So it's simply C and D complement. Next, how about this group right here? Let's see. For that guy, A is a 0, B is a 1, C is a 1, D changes, E is a 1. How about this guy? A is a 1, B is also a 1, C is a 0, D is a 1. The last group here, A changes, B is a 1, C is a 0, D is a 1, and E is a 0. Let's see, there's a question in the chat box which says, couldn't you do a single grid with 3 variables on one side of the grid if you write the binary like this? Uh, I'm not sure what you mean, Alex. Can we circle back to this at the end of class, maybe, because I have a couple of more points that I want to discuss, and then we'll come back to this. So this is a 5-variable K-map where you are able to treat multiple 4-variable K-maps. You can treat them like they are layers on top of each other. All right, that will be helpful, Alex. Yes. So you can treat them as the two 4-variable K-maps as uh, layers that are resting on top of each other. The first layer is when the A is 0, and then the second layer is A is 1. And you can think about making those bigger groups. So I hope that was helpful. Um, let's move on here. Let's see, 4-variable is done, 5-variable is done. We talked about the K-map usage. We talked about numbering the cells to make things much faster. Let's talk about the simplest product of sum expression. So for simplest product of sum expression, the entire story is going to get reversed. Now you are going to say, I will focus on combining the zeros. Instead of combining the ones, you are trying to combine the zeros instead. So let us start with the same question. Can I make a group of 16 zeros? The answer is 0. No, you can't make a group of 16 zeros. Can I make a group of 8 zeros? No. Can I make a group of 4 zeros? Yes, a couple of them. Let us see. The first group of 0 is right here. This is very clear. Oh, come on. The second group of 4 zeros is right here. This 0 cannot be combined with anyone. And the left out 0 can only be combined with this. I have covered all the zeros, so I'm done. I'm simply going to write the expressions for this. There is going to be a change in the way you write expressions, so I want you guys to notice this. For the top left group of 4 zeros, A is 0, B changes, C is 0, D changes. So the sum term is going to be A or C. Next, for the second group of 4 zeros, A is 0, B changes, C changes, D is 1. So you write D complement. Next, similar to the differences between min terms and max terms. All right, next let us write it for this group of 2 zeros. What do you have here? You have A changes, B is 1, C is a 1, D is a 1. Next, for that guy, A is a 1, B is a 0, C is a 1, D is a 0. So the simplest product of sum expression in this case is going to be A or C, A or D complement, B complement, or C complement, or D complement. Done. Questions about this example here? Next, I want to actually ask a question here. What about don't care conditions in POS? Right. So when you're trying to find the simplest product of some expression, how do you deal with don't cares in that situation? Well, the story is going to be similar to before. The answer should be what? Treat the don't care as a 0. Treat don't care x as zeros only if it helps make a bigger group of zeros. Otherwise, treat the don't care as ones. And you have to, the goal is, or the objective is, that you need to cover all zeros in this case. Yes. So you group the x only when it helps you make a bigger group. That's it. Otherwise, you leave it out. All right. So let's see. I want to do a couple more examples here, maybe one or two, in which I want to talk about the connection between product of sum and how you can you can reach the simplest product of sum using a different way. So what I'll do is I will start off with a truth table. So this is the title of this slide is also the same as this. Copy and paste it here. It's still the simplest product of some expression, but we are going to derive that in a slightly different manner. So what I'll start off with is a truth table. So let's say I have this guy, I have this guy, and then let's say I have A, B, C here and F here. So I've got 0, 1, 0, 1, 0, 1, 0, 1, 2 zeros, 2 ones, 2 zeros, 2 ones, and then I've got 4 zeros and 4 ones here. All right. Now what I can do is I can arbitrarily put some ones and zeros in the output side. Say I have 0, 1, 1, 0, 0, 1, 1, 0, 1. Sure. Right. So I've arbitrarily selected some logic function with some truth table. What I'm going to do is I'm going to get the simplest. So step 1. Find simplest SOP. So first I'll try to find the simplest sum of product expression for this, which means that I have to lay out a 3 variable K-map. 1, 2, 3, and then there, and then I've got A here, B here, C here, 0, 0, 0, 1, 1, 1, 1, 0, 0 and 1. All right, so how do I enter? I enter 0, 1, 1, 0, and then 0, 1, 1, 1. All right, so if this is the case, can I make a group of 8 ones? No. Can I make a group of 4 ones? No. Can I make a group of 2 ones? Yes. Yes. Now, where should I combine this 1 with? Should I combine it with 1 here, or should I combine it with 1 here? Should I horizontally combine it or vertically combine it? Alan, we are doing SOP as a step 1. Our final goal is to get simplest POS. Just follow along, just bear with me for a few more minutes. You will see the connection. Let's number this so that I can ask a better question. Should I combine cell number 7 with 5 or with cell 6? Well, if I combine it with cell 6, it will still be a group of 2. And if I combine it with cell 5, it will still be a group of 2. So in terms of variables, it will still be the same. The number of literals for that particular group will remain the same. However, I wanted to you guys to realize the point that I made at the beginning of the lecture, in which I said simplest forms are not unique. So it really doesn't matter which one you combine here. You can do this way or you can do this way. You have to select one. But you have two choices here. Both of them are equally correct. I can maybe go this way. And then in a different color, perhaps green, I can show you the alternate form. So I will leave out the green for now. I will focus on the blue. But green is also an option. All right, so let me write out the expression here, simplest SOP expression. What do I have? F equals, for there is A 0 changes, B is 1 and C is 0, or for the wraparound I have B is 0, C is 1, and then for the group of 2 ones we decided at the very end, A is 1, C is also 1. So once you have the SOP expression, the second step is this. Let's do this. This was find simplest SOP for F complement. So I'm going to do a little bit of a shift here. I jumped the gun on. So let me treat F as 1. All right. So I started out with F. I should have started out with F complement. So I've switched around my logic function a little bit so that I don't have to change much. F is now this, so that F complement is this, and then I'm trying to find the simplest SOP for F complement. Once I do that, I'm going to do De Morgan's law. Complement both sides. So when I complement both sides here, what do I have? F complement equals B and C complement, or B complement and C, or A and C if I complement both sides, I get that and that. My left hand side is simply going to become f. My right hand side, you are going to use De Morgan's law to write b and c complement. This will become and, which will be a product of some expression, the simplest product of some expression. So you can reach the simplest product of some expression for f in both these ways. So this is f. This is my final answer here. So I started out with some f. I wrote f complement here. Then my first step was to find the simplest sum of product expression for f complement. So I filled out the truth table, the K-map for f complement, combined the ones because SOP, and I wrote an expression, simplest SOP for f complement. Then I applied De Morgan's law. So I complemented both sides. So when I double complemented the left hand side, it became f. And I got on the right hand side, by application of De Morgan's law, a simplest product of some expression. So you could directly combine the zeros. And another way of thinking about that is to start out with the simplest SOP for f complement and then apply De Morgan's law. You reach the same answer. All right, questions about K-maps, 2 variable, 3 variable, 4 variable, 5 variable, use or don't use of don't care conditions, and simplest SOP and simplest POS expressions. I hope you guys are enjoying the K-maps. This particular topic tends to be one of the more liked topics throughout the course, because how effective it is and yet so simple. And it is graphical, which everybody likes. So, to be honest with you guys, one of the things that, when I took this class after many, many years, if you go back and ask engineers who have taken, a digital logic design class 10, 15 years ago, or even 25 years ago, you ask them what they learned, they probably will tell you K-maps as the first answer. So this tends to stay with you for a very long time. All right, so let's see. I'm going to stop recording here.